the aggregate is additive. So the total influence is the sum of the influences on along each path. Now this figure you must remember, because we're going to keep coming back to this, not just in this class, but several classes. Because this is the basic concept we're going to use anytime we compute derivatives for the purpose of computing this particular derivative, which is the derivative of the divergence with respect to the parameters, right? So let me start off first by a few preliminaries. We're going to spend some time on this because this has to be understood. I'm showing a tiny two-input network for illustration. So here we have the input has only two components, x1 and x2. And I have two layers, two hidden layers. Each hidden layer has only two neurons. And then I have a single output block. So now again, remember what each neuron really looks like. Each neuron first computes an affine combination of its inputs. That affine combination is then put through an activation function. Remember? So I can expand each neuron out like so. So each big yellow ellipse shows a single neuron where it shows the individual steps of the computation. The first step, you compute an affine combination of the inputs. The second step, you transform this. So I should have, in principle, I should also be showing it here, but here I have not actually drawn the yellow ellipse. It's really the same thing. I have also done an additional thing. I have sort of added an extra 1, and why am I doing that? That's the bias, right? I'm just sort of factoring in the bias into the 1. I don't need to explicitly show you the extra 1. Sometimes, very often, I just won't show it, it's implicit, right? So now let me begin labeling my variables. So here are my inputs, x1, x2, and x1, which could be x3 if you thought of it as an additional component to the input. The weights have a superscript. The superscript indicates the hidden layer that the weight is actually connecting to, any edge is connecting to. It has two subscripts, so weight 32 means that this is the weight of the connection from the third component here to the second neuron over here, right? So here, for example, weight 22 with superscript 2 means that this weight connects to some neuron in the second hidden layer, and it connects the second neuron and the first hidden layer to the second neuron and the second hidden layer. So you get the idea, right? Now, but these are not the only things that we must worry about. To be very clear, we also need to, so here again is the complete figure, and so now in addition, we want to label other stuff. Have I labeled it? Yes. You want to label every single variable that is being computed when you're actually processing any data. So these are the weights, these are the affine combinations. The z's represent the affine combinations of the inputs to any perceptron. The y's are what you get after the affine combination, which is z, has been processed using the activation. We're distinguishing between the two. And so this is the entire the z's again, they have a subscript which represents the neuron itself. I've numbered the neurons, right? And it has a superscript which represents the hidden layer. Now, so obviously, when you get to that final layer, which I'm going to be calling the nth layer, that output is just the output of the network itself. So I'm just representing it as a output. And what do we actually want to minimize? The divergence between this y and some desired output b for the input x. So what we really want to know is what is the derivative of this divergence with respect to, say, this parameter. Now it's a long, complicated connection over here, but as it turns out, it's very trivial to compute. So to do this, I'm actually going to try to do this on the board, and you guys are going to help. So this will help you all stay awake. And I have lots of friendly little pieces of chalk, so if you don't respond to me, I'm going to toss it on your head. Now, let's start with this figure here, which is a simplified version of exactly what of a network, and this is the same thing that we have on the board. So here we're considering a two-component input, x1 and x2. I'm not explicitly representing the bias. Now, here's how the processing would happen, right? So let's say I have two hidden layers. The first thing you're going to compute is the affine combinations, the z's, and have subscripts indicating the specific values. Trying to make them all unique. I'm assuming that the weights here are the same as the weights here, just different unions. But these are going to be processed by some activation function to give you the y's. Those y's are going to be combined to z's using some additional weights. They are processed again to give you more y's. These are combined using some weights. That's processed using another activation function. And finally, this d over here actually computes. I need a brighter chalk-headed, I don't have it. This d actually computes the error. So I've sort of color-coded it. The symbols in white are all parameters. The symbols over here that are in blue are things that you actually compute. And the symbols in orange are the input and the output respectively. So you see the distinctions. The colors tell you what kind of variables I'm actually trying to look at. Now what I want to compute is the derivative of this term, let's say, with this guy. How much does changing this term a little bit affect the error? So how would I go about doing this? Now remember, before we get to this, remember our chain rule. Our chain rule was, suppose I had y equals g of h of, say, k of x. The way you computed it was dy over dx. Again, I'm talking about scalars, so I can use this notation. Was dy over dg. So how much does actually dy over dh? So how much does changing this guy affect y? And then how much does changing this term affect h? And then finally, how much does changing this term affect k? So observe the sequence of operations over here. The sequence is very important. Now, in the scalar case, it really doesn't matter, but when we begin talking about vectors, this sequence really will matter. So first, you're looking at the outermost function, and you're just asking yourself, how much will changing the argument to the outermost function change the output? Then, changing the outermost function requires changing the argument to the outermost function, which means changing the argument to the argument. So the next one is how much does this get influenced by k? And then the next one is, okay, if you're going to change k, you have to change the argument to k itself. How much does a change in k respond? How does a change in k happen if I change x? So that you're going from the outside in. Keeping that in mind, what is the outermost function over here when I'm thinking of E as the final output? D. So what is the first derivative I need? Anyone else? What's the first derivative I need? So you back there, you have your name badge. Yeah, okay. So Shivan, what is the first derivative I would need?
D by d.
So the first thing I'm going to need is dE over dO, which is d prime O, right? The very first thing I would need is to take the first step back, because the outermost function is d, which in our case is the divergence function. So I need to compute dE over O, and this is the derivative of this function computed at the current value of O. Keep that in mind. It's computed because the location of O changes the derivative, does it not? So it's computed at the current value of O. Now, what is the next thing I would compute? So from here, I can now compute this is the next inner guy, right? So that is going to be dO over dz5 using the chain rule. That is going to be dO over, wait, no, dP over dO. Okay, so dP over dO times dO over dz5. Can you guys read this? Can everybody read this, right? So this is working my way backwards. That is going to be what was dE over dA? That was d prime O times F prime z5. This was easy, correct? I'm just taking a step back. Each time I'm just chaining things on when I'm computing the derivatives. And it's always convenient to draw these influence diagrams. They should have taught this to you in school. And the fact that they didn't is a shame. Because when you draw these things out, it's very easy to see how you're chaining the derivatives, how you're just multiplying things going outwards in. Right? Now the next thing I want is what? Changing this changes a bunch of things. We change a bunch of things. We change a bunch of things. So I would like to compute now the derivative of E with respect to this term, right? Y4. What is that going to be? So what is the derivative of E with respect to Y4? You can just follow the chain back, right? So you can start from here. You're going to compute the derivative of E with respect to O, derivative of O with respect to Z5, derivative of O with Z5 with respect to Y4. So you can just work your way back through the chain. And so that's going to be d prime O times F prime Z5, right? And what is the derivative of Z5 with respect to Y4? Just the weight, because Z5 is just a weighted combination of its inputs. It's affine, right? So this is going to be W.r.t in this case. And I can also compute similarly the derivative of E with respect to Y3, which is going to be d prime O. So observe that I don't need to recompute this term every time, right? Although I'm writing it out like so, I could have just written this as the derivative of E with respect to Z5, right? Times W31. Make sense? So far so good. So now I can, but then now I can go back and I can compute the derivative with respect to Z4. How would I do that? Again, I can follow the chain backwards, right? And if I follow the chain backwards, what is the chain of influences over here? Z4 influences Y4, influences Z5, influences O, influences E. So if I work my way backwards, the derivative of E with respect to 4 times the derivative of 4 with respect to Z5 times the derivative of Z5 with respect to Y4 times the derivative of Y4 with respect to Z4. So this is easy again. So I can just, if I want to have the derivative with respect to Z4 and Z3, I just have to multiply this again with F prime Z4 and F prime Z. This is easy, right? Now, so for now, let's assume I want to compute the derivative of the error with respect to Y2. Now, what do I need to do? So if you look at the influence, this is where this business of the influence diagram comes in, right? If you look at how Y2 influences E, there are two distinct pathways through which Y2 influences E. So Y2 influences Z3 and y2 influences z4, and each of those in turn influence, correct? So which means if I want to actually compute the derivative of e with respect to, do I have another board item? If I want to compute the derivative of e with respect to, wait, let's stop here. y2, what is it going to be? It is the sum of two terms, one along each of the two yellow lines, correct? So that's going to be dE over dz3 times dz3 over dy2 plus dE over dz4 times dz4 over dy2. Make sense? Right? I'm just following the complete chain of connections over here. And so, and these derivatives, of course, we know. What is the derivative of z3 over with respect to y2? What is this derivative?
W2 the weight.
That's just the weight of the connection. Z is an affine combination of the w, of the y's, right? So this is going to be, what was this weight? y2 z3 is w21, right, in my case. And this is going to be w22. And so I can now do the same thing. Make sense to everybody? And just to sort of emphasize the point, now suppose I want to compute the derivative of e with respect to y1. What are the chains over here? So if I want to compute the derivative of e with respect to y1, what are the chains of influence I have to follow? There are two of them. So that's, this goes here, and that connects to e, right? And this goes here, and that connects to e. Correct? And so the corresponding derivative over there is got to sum over both components. Now I'm going through this in a little bit of painful detail because this means I can take a shortcut in the next several slides. So this is going to be, say that dE over dy1 equals dE over dz3 times dz3 over dy1 plus dE over dz4 times dz4 over dy1. Right? And these derivatives can be replaced by, what are these guys? These two terms. Again, they are just the weights. So I can write these weights down. This is going to be, what is this one here? W11. And this one here, what is this? W1. So I can actually write this in shorthand notation. I can write this as dE over dy2 is summation over all the edges, outgoing edges, right? Edges, dE over whatever z you had at the end of the edge times the weight of the edge. Just taking a very crappy shorthand, but you get the idea, right? So, but basically what's happening is that at each point, you're looking at all the ways in which the signal can go out, and then finally influence the, what is the thing that you're bothered about? The error, the divergence, right? And so you're looking at how all the ways in which the information can go out and finally influence the divergence. You're going to have to take derivatives over all of these paths and add them up, and that just ends up being, so the cool bit is that the derivative of the error with respect to this y is just a weighted combination of the derivative of the error with respect to these z's. That's what we saw, right? And the weights are the outgoing edges. Weights of the outgoing edges to these z's. Anyone not get that? This is kind of so if you get it, the next several slides, I can skip the next several slides in 4 minutes flat. So it's very important that you actually get this stuff, okay? Yes?
But we want the divergence with respect to the weight.
Yes, thank you. So how do I compute now? So why did I need to compute the divergence with respect to these y's and the z's? So what is the derivative of the error with respect to, say, this specific weight, dw22 in the second position? What is the derivative of the error with respect to that guy?
dz4 over dv times d.
Again, so you have to think about this. So if I think of this as whatever I'm going to modify, how does this influence E? That's a chain you're going to have to follow, correct? And that is going to be, this term influences this, and that influences E. Right? So that is going to be dE over dz4 times dz4 over dw22. What is this term over here? That's just y2, right? So basically, just using this very simple notion of following the chains of influence, you can compute all the derivatives all the way back through the network. So everybody get that? Because now I went through like 25 slides in 40 seconds, right? But before that, something else. I computed, here's another key piece that is important to know. Can I just directly compute the derivatives, or do I need to do something else first? The derivatives are computed at a specific location, right? So this term requires knowledge of Z3. So in other words, in order to compute the derivative of an error with respect to with respect to any given parameter for a single input, I need to know what the intermediate values in the network were for that input. Make sense? Right? I needed to know what this guy was. So which means that the first thing I must do when I begin trying to compute the derivative is to compute all the intermediate values going forward and the output, because only when I know the output do I know the error, and only then can I go back and compute my derivatives, right? So that's what you will do. The computation of the derivative requires intermediate and final output values of the network in response to the input. If you don't have these, then these terms, this f prime, which was intermediate derivatives of along the chains of influence, those things cannot be computed. And so we begin this way. There's a network again. I'm calling this the scalar formulation because we're going to look at it in vector form. Okay. So the first thing you would do is I've redrawn it, showing every z, every y, and so on. First step, you're going to compute, you're going to process it going forwards, which means you compute the affine combination of inputs to the first hidden layer. You go through all of the z's, so you compute this for all of the z's, right? I mean, all of the percentropes in the first layer. Then process those using the activation to compute the outputs. But then once you computed the outputs of the first layer, those things can be used to compute the weighted combination, the affine combinations that are going to the second layer. And then from thence you can compute the activations at those points and keep going forward all the way till you actually get the output of the network. The forward processing is very simple. it's just weighted combination, affine, weighted combination, affine combination, activation, affine combination, activation. And you can do this if you were writing code, you probably loop through all of these guys first, then compute these guys, then loop through all of these guys and compute the inputs and outputs and so on, and go all the way to the end. Easy now. If you were writing loops, which you would. But then once you've done this, so here is the little pseudocode for how you would do this. Let's skip the pseudocode. Just point out that we're going through each layer, and for each layer we're going over all of the perceptrons, computing the affine combination, and then passing the affine combination through the activation for that layer, which can be different from layer to layer. And then we start off with the derivatives. The first thing we do, we define the entire network. We have the divergence function. We have the divergence. I can work my way back. First, compute the derivative of the divergence with respect to the output of the network, right? And then I can compute the derivative from there to the affine combinations that go into the final activations. Then from there, I can work my, so again, observe that when I'm doing this, I'm using a z value that was computed in the forward pass, right? Then from there, I can work my, this is the derivative of the activation function. And then from there, I can work my way back, go down, and in each case, I'm just going to be computing, I'm summing over all outgoing edges of the derivative of the divergence with respect to the z's times the derivative of the divergence of the z with respect to the y, which is going to be just a weight. So it's a weighted combination. I've done something very silly over here. I've written them in wrong order. It doesn't matter when I'm doing this with scalars. With vectors, it will matter, as you will see. So, and then once I have those, I can take the derivatives one step back and keep doing this all the way backwards, right? And in the process, I can also compute the derivative with respect to the weights, exactly as we just saw. We're basically following the same procedure that we just saw. So the slides have all of the detailed, painful, ugly notation. I don't recommend going over the slides in class, but I do strongly recommend going over the slides offline. Take a look at them, work your way backwards, and make sure that you understand what really is going on. Okay? I said 4 minutes, I found that here I am 4 minutes now. And so we're done. Beautiful. We've just covered what is called backpropagation or error backpropagation. Why are we calling this backpropagation? Because if you actually compute the derivatives, you're computing the derivatives outside in. In the case of the network, the outside is the outermost, the outermost value obtained, which is going to be the error, and then you're working your way backwards through the network when you're computing the derivative. So it's error backpropagation. So now again, why error backpropagation? What if I'm computing the error back? What you're actually propagating backwards is the derivative, so you should be calling it error derivative backpropagation. But there's a reason for calling it error, which most people won't recall. So here is the backward pass. If I were actually writing code for the backward pass, first I will be computing the derivative for each input. This is again for a single input. Remember, all of this is about computing the derivative for a single input, right? So what you're going to compute the derivative of the divergence with respect to the output of the network, and then you work your way backwards, and at each layer you go over all of the neurons. First compute the derivative with respect to the output of the neurons, which is just going to be a weighted combination of the derivatives of the downstream in affine inputs to the downstream perceptrons, and then take a step back and then compute the derivative with respect to the affine input to the perceptrons. Now, this kind of looks at, and in the process, also compute derivatives with respect to the weights. Now, again, go back and look at the slides carefully, but what you will observe over here is that the pseudocode here uses ugly notation. It's got these does on top, partial derivative symbols on top and bottom. But if you compare it to what happens when you're going forward through the network, the two bits of code look effectively identical. And that's because what you're doing is when you're going backwards, you're computing a weighted combination of the next layer and then taking it backwards through the activation. Whereas what happens when you're computing the output of the network in response to the input during the forward pass, you compute a weighted combination of the output of the previous layer and then taking it forward to an activation. So the process is literally, almost identical. It's very analogous, right? So it's in fact, in terms of coding, the two, if you wrote it with ugly, silly loops, the coding is going to look very simple. Now, questions? I guess not. Yes.
I was just wondering if you clarified if you go back to the last slide. How do we get the y sub j, which is the k when we're talking about with respect to the weight? I just didn't quite catch it.
So this term,
Yeah, on the bottom line.
So that's basically, remember what we said that before you compute the derivatives, the first thing you're going to do is pass the input through the network.
Yeah, so I understand where we get the value from. Why is that with respect to the weight?
So that is because you had z equals w times y, right?
Right. Yeah.
So the derivative with respect to the weight is going to give you the y, the derivative with respect to the y is going to give you the which means that you can actually even compute the derivative of the error with respect to the input to the network. You can work your way all the way backwards. Now, special cases. We've assumed so far that the computation of the output of one neuron does not directly affect, in the figure and all the examples that I've done, does not affect the computation of other neurons in the same or previous layers, right? And if you assume that the outputs of neurons only combine, in an affine manner, and we've computed, assume that the activations are all actually differentiable. All of these assumptions can be invalidated, and the whole process still holds. For this, you're going to have to look through slides. But look through the slides. I won't actually go through it, but the point I want to make, here's a key bit, is that very often you're not going to be computing the outputs perceptron by perceptron. You're going to be looking at a bunch of inputs and computing a bunch of outputs. So here, these are what I would call scalar activations. Modifying one z affects only one y, right? So every affine combination is being individually processed by an activation. You can have other situations where they are jointly processed, and some of you have already, those of you who have looked at the homework, have actually encountered one of these. What was that? Softmax, right? If I change one guy, it changes everything. So now, in a scalar activation case, I can just say y equals some function of z. But if I'm thinking of collections of inputs affecting collections of outputs, it's better represented in vector form, where I say that this vector of outputs is some function of the vector of inputs. So it's just a vector notation. And once I use this vector notation, when I have a scalar activation, each z only influences a particular y, right? So if I want to compute the derivative of the error with respect to a z, I just need to compute the derivative of the error with respect to the corresponding y, and then multiply that by the derivative of this y with respect to the z. But when I've got vector functions, things change. Now we have to go back and look at how things influence the output, correct? So here, every one of these z's influences every one of these y's, correct? So how would you compute the derivative? And again, the number of outputs doesn't have to be the same as the number of inputs to a vector activation. So which means that your vector function doesn't have to be dimensionality of 10. It could increase or decrease the dimension. So given this, here is the derivative rule for scalars. It's very trivial. The derivative of the error with respect to any z is simply going to be the derivative of the divergence with respect to y times the derivative of the divergence with respect to z, which is the affine, right? This was very easy. If I've got a vector function, now the influence is much more complicated, right? Because this y, so what you've got over here, I should have been a little more explicit in my figure, that I have a vector function, I have all of these z's going in, and I have some bunch of y's going out, and then I have a final error, and or this is my divergence, right? Every one of these outputs influences the divergence, and each z influences every y. So if I want to compute the derivative of this divergence with respect to the z, I have to follow all of these chains and sum over the lot, right? Which means that I have to get the derivative of, I'm summing over all of these outputs, and the term I'm summing is the derivative of the divergence with respect to the y times the partial derivative of y with respect to z. But I must sum over all of the outputs. If I don't, my final derivative is going to be wrong. That clear? So now exactly how this works out for different kinds of vector activations is on the slides. I have several slides worth of information. These will be in the quiz, and they will be in your assignments. Take a look and make sure to go through it because it's kind of important. Now, just in case you didn't hear my words, I'm also stating it on the slides. So here is the overall training by Backprop. You'll be initializing all of your weights. You'll initialize the total error. Then you're going to loop within each iteration, right? You remember, we keep updating iteratively. Within any single update, you will loop over all your training instances. You have a forward pass where you pass the training instance through the network so that you can compute all the intermediate values. And then you have a backward pass where you work your way backwards and compute the derivatives, all the partial derivatives with respect to all the parameters. And you would accumulate these because you want to get the total derivative over all of the training instances, but then eventually you must divide by the number of training instances because what you're really interested in is the average error. And so here is the basic ability. This is very straightforward. If you want to write down the gradient descent learning rule for neural networks, it's pretty much just this, what I have on the slides, where you need some other separate routine to perform the backpropagation. Now this, observe that here I've literally written it down in terms of what happens at individual neurons, right? So I've written this in what I would call a scalar formulation. Neuron by neuron, what is the computation you're going to perform? Parameter by parameter, what is the computation you're going to perform? And if you were to write code the way I just explained it, you'll be writing loops, and what happens when you write loops? Sucks. Somebody said sucks. Somebody have a more polite word?
Slow.
Thank you. Go ahead. Sucks is better. It's a much more, in fact, sucks kind of doesn't quite describe what happens. It's even worse, right? So what you really want to know is, can you actually look at it more in terms of block computation? So we will look at what happens in vector terms. And now, if I'm beginning to state things in vector terms, I have to define my derivatives in vector terms. Is there anybody here who can tell me the chain rule for vector functions? Everybody knows the chain rule for scalars, right? But what are you really doing when you're speaking of vector functions? Again, we're using the chain rule. Nothing has changed, right? So we're going to start off. I will go through this. I would normally not do this because I see so many of you actually struggling with this bit in your quizzes and assignments. Maybe it's worth my time. Otherwise, I just designated it with the slides and asked you to look it up. So here's how I can write it. Consider a layer network. So I have some x's. They're all being operated on to compute affine combinations. So if I'm doing that, I can write the entire thing as one single vector formulation. So I can write all of my x's. These are the components of the input. So these are the x is a d-dimensional vector. So I can write my x's as a single vector. I can write the affine combination of x's as a vector z. And I can write the output of these activation functions as a vector 1. You see what I'm doing over here, right? Now there are weights which are used to combine the inputs to produce the affine combinations. I can write those weights down as a matrix W. And notice something specific. Each row of weights corresponds to all the weights going to one particular unit. So when I write it like so, I can actually write over here. Does this work? Yeah. In fact, I don't need to work it out. You will actually see that z equals weights times the weights matrix times y plus d works out to the correct term scalar by scalar. Right? So what this really means is if I'm writing this, maybe it's what. So I'm writing z1 through z3 equals w11, w21, w n is the number of inputs, right? So the second one is going to be w21, w12, n2, and this is going to be x1 to xn plus v1 to vk. Now, if you look at this, the first component times the first entry plus the second component times the second entry. So this literally means zi equals summation j w.r.j xj plus v, right? This is exactly what you're going to get term by term if you work this out. So this works. And now I can say y is a function that operates in the vector of inputs, but y is also a vector. So there's a vector input and a vector output. Caleb, those questions?
Yeah, this is different from before because x it's here is n by the feature.
Don't wait. I'm using column vectors. The homeworks you're probably writing Python code where everything is a row vector.
Okay.
So things are transposed, right? So you're going to have to transpose things in your head and all the orders and make the appropriate corrections when you write code. Yes.
In slides, WK goes from layer K to K plus 1, right?
The K minus 1 K.
So why are the dimensions?
So I may have some errors in the errors, please point them out. But this is going to be the dimensionality of the input. Right? So maybe I have some, so that's this line. So this should have been, so this is the dimensionality of the input. Maybe I've flipped things over here. Alright. And this is the dimensionality of the output. And this again is the dimensionality of the output. Right? Right. So if I'm doing a forward pass, if there are errors, can somebody post a note in Slack?
Sure.
So during the forward pass, I just say y0 equals x. For the first affine combination, is simply going to be w1 x plus v1, where w1 is the first weights matrix. Then I process the whole thing using some function. Then the next affine combination process the whole thing. So observe something that's happening over here at the bottom. This first output is a function which is, I can think of this as a vector function applied to an affine combination of inputs. The next one is an affine combination of the output of these guys. So now we're beginning to see nested functions. Right? When I go all the way to the end, what I'm going to get is a big nesting of functions. But the computation itself is very trivial, very straightforward, going forward. And so the entire forward operation, when you write it in vector form, is simply going to be this very trivial set of equations. You first compute the affine combination of the outputs of the previous layer, then you compute the activations applied to this affine combination, and keep going through all the way to the end. So here's the overall forward pass. Things get a little more fun when you want to compute the derivatives. So the divergence is a function of the output. In other words, the divergence is also a nested function. Correct? It's a function of 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 a function. And when you do that, how would you compute the chain rule? Yes, you're going to compute the derivative with respect to the outermost function. Then you multiply that by the derivative of the outermost function with the next outermost function, and keep following that rule down. So that's the chain. That is the process. Again, this is specific to the column vector notation that I'm using. If you change things, things will change a bit, right? But this is convenient. So first, let's begin defining our derivatives. And remember, I was giving you this whole gobbledygook about influence diagrams. That just kind of works out beautifully when you think of vectors. So I have a vector output. I have a vector. So this is, I'm speaking of just the affine, the activations. I have a vector output y, which is a function of a vector input z. So what is the derivative of the vector output y with respect to the vector input z? I can represent that as this matrix, where each row, so observe that each y is a function of this entire vector, right? So I can compute the derivative of this y with respect to that vector. What do we call that derivative? No, it's a scalar, right? We call it a gradient, remember? And what was the, and using our convention, what was the dimensionality of the gradient? Was it a row vector or a column vector? No, how did we define it? The row vector, right? The derivative was the row vector, the divergence. Because remember a basic definition for derivatives, we said delta y equals whatever the derivative times delta x. So the delta x is a column vector. What was the derivative? It was a row vector. This was the way we defined it. So this first term over here, this first row is just the gradient of y1 with respect to this vector. The second row is the gradient of y2 with respect to the input vector, and so on. So that matrix is basically a stacking of the derivatives with respect to each of the derivatives of each of the components of the output with respect to the entire input. And this is the reason I use the horizontal notation for derivatives. It stays consistent with the definition of Jacobians, as we will see. So I just stacked all the divergences, and this is the derivative of a vector function of a vector input that produces a vector output, right? And we call this a Jacobian. This is called a Jacobian. Fine. So look at what happens when I have a scalar activation function. I have a scalar function, bunch of scalar functions, which I'm just assuming is vector. Then for the first term, y1, these partial derivatives are going to be 0 because y1 doesn't depend on all the subsequent z's, right? For the second guy, only the second term is going to have some value, the rest of the partial derivatives are 0. So this derivative is going to be in diagonal matrix. In the more generic case, it's so, and the diagonal matrix, the diagonal entries are just the derivatives of the individual activation functions. In the more generic case, it's going to be a full matrix, bunch of partial derivatives. Everybody get what I'm talking about here? Straightforward, right? So, I'm just introducing definitions, nothing fancy so far. But then let's go back and look at this. If I look at z equals w times, oops. So if I just say z equals w y plus b, right? And these are, w is a matrix, z and y are vectors. What is the derivative of y of z with respect to z? Now, what this really means is zi equals summation j wij yj, correct? So the gradient of zi with respect to y, which is all of the y's, is going to be the partial derivative of zi with respect to y1 partial derivative of zi with respect to y2 and so on. And this is simply going to be w. I should call this di. Okay. So this is going to be w1i, w2i, and so on. If I stack these up, this is simply going to give you the weights matrix itself. So you don't have to actually work your way through this. The shortcut, what happened to my picture? So the shortcut over here is that if I take the derivative of z with respect to y, the Jacobian is simply going to be the weights matrix. What would the derivative of z with respect to b be? It's an identity matrix, right? So again, I can think of it almost as I think of scalars. So this is very easy. Now let's look at nesting. Okay. So if I say y equals some function, vector function of another vector function of a vector g. So what is the derivative of y with respect to x? So I'm going to claim that the Jacobian of y with respect to x is the Jacobian of y with respect to g times the Jacobian of g with respect to z. Basically, I'm using the same chain rule that I used earlier for scalars. And it's very easy to show that this is the case. I can just write z equals g of x. I can write y equals f of z, right? Using our rule, that delta z is going to be the Jacobian of z times delta of x. This is how we always define derivatives, remember? For any function. And I can also say that delta y is going to be the Jacobian of x times delta z. This is again the same, this is literally the definition of derivatives, remember, right? So if I replace this delta z over here, then I'm going to say delta y equals the Jacobian of y times the Jacobian of z times delta x. So this term over here is the derivative of y with respect to x. You see how the whole thing sort of chains up? Things keep getting added on to the right. Now, even if it's a scalar function of a vector input, the same rule holds. So if the output b over here is a scalar, all that happened was that this first Jacobian is not really a Jacobian anymore because the output is a scalar. This is going to be it's going to be a gradient, right? And a row vector times a matrix is going to give you a row vector again. Now observe that the dimensions hold. So this is a scalar, x is a vector. So you expect the derivative of b with respect to x to be a gradient, a row vector. Remember? And I'm going to say that is the derivative of d with respect to g is a row vector, it's a gradient. Derivative of g with respect to x is a Jacobian, it's a matrix. What is a row vector times a matrix? It's a row vector, the dimensions hold, right? But you also see how the chain rule holds. And this basically, I have it on the slides over here, but it's going to be the derivative of the outermost term times the derivative of the next inner function times the derivative of the next inner function, and so on. You can work your way all the way through. Yes?
So, in the homework, then you have to flip everything.
Exactly, because you guys are using rows. I mean, you're using the wrong programming language. You should be using Fortran. So,
may I ask, why is that in Python you have to, why don't you just flip it in Python?
It's just convention. It's how you think about rows in your in memory, right?
Oh,
So you call it rows. If somebody had decided to call them columns in memory, then all the notation would have changed. Somewhere a long time ago, some person decided that we're going to call them rows in memory, and then the convention stuck, and you guys are stuck with bad math. So now, special case. This is really important again. So let's say I have d is a function of an affine combination. What is the derivative of d with respect to y? That's first going to be the derivative of d with respect to this affine combination, which is the gradient, times the derivative of the affine combination with respect to y. Correct? And the derivative of z with respect to y we just saw was the weights matrix W. So if I have the derivative of d with respect to y, in this case, that's going to be just the gradient of d with respect to this inner term times W. So this is easy, nothing big. Similarly, what is the derivative of d with respect to b? That's going to be the derivative of d with respect to z times the derivative of z with respect to b. And that's just simply because the derivative of z with respect to b is the identity matrix, that's just the derivative with respect to z itself. This third term is not very obvious, right? What is the derivative of d with respect to w? And here, all of the little intuitions you might have developed kind of break down. They don't really, but they seem to break down in the sense that if I have y's, so I have a vector y, y1 to say yn, and then I have some combination weight matrix, and then I have some z over here, and then this goes off to e, right? So then the derivative of e with respect to w, actually, I can even think of the derivative of e with respect to w is going to be y times the derivative of e with respect to z. So here is the crazy bit. How does this happen? It turns out that the derivative of z with respect to y is just the derivative of z with respect to w just happens to be y, but it ends up becoming a tensor if you work your way through the tensor arithmetic. What you find is the derivative of e with respect to this w is this input times the derivative of e with respect to this guy, which is a row vector. So you have a column times a row, it gives you a matrix. Okay. So this is something I really want you to remember. I'm not going to spend time deriving it. It's straightforward because it would take me 20 minutes. But you get the idea, right? This is the one-off thing that you must remember. So this term, this column, post multiplied by the derivative of e with respect to z. So we've set our basics. Now let's go back and look at this guy. Very clearly. I'm just going to compute my derivatives backwards. If I want to do my backward pass, first I compute the derivative of the divergence with respect to y. Right? Easy. This is just, what would this be? That's a gradient. Correct? Then I want to compute the derivative with respect to z, which is going to be what? The derivative with respect to y times the derivative of y with respect to z, which is going to be a Jacobian. Right? And then if I want to compute the derivative of divergence with respect to this guy, what happens? So I post multiply the derivative of this term with respect to these, which would be the weight matrix. Right? And then if I want to take a step back, what do? I multiply this by the Jacobian of this term with respect to this guy. Right. So I'll come back to this. I can just take a step back, and that's going to give me, I multiply the derivative of this term with respect to y, and multiply it by the Jacobian. So I keep multiplying it, and then I take a step back. That's just not going to be multiplying it by the weight matrix. So every time I take a step back, I'm just multiplying it by one term, right? Multiplying it by one term, which is either the weight matrix or a Jacobian matrix. Right? It's just the straightforward chain rule in vector terms. It's what I spent time on, just a few minutes ago, explaining the chain rule for vectors. Very straightforward. And in between, we also need to compute the derivatives with respect to the parameters. So if you're computing derivatives with respect to biases, that's simply going to be the derivative with respect to z, as we saw. But suppose I want to compute the derivative of the divergence with respect to this weights matrix. That we saw is going to be this output vector times the derivative of z with respect to of the divergence with respect to z, using the rule that I have on the board. Right? I mean, you might find it a bit much to swallow all at once, but the rules are very straightforward. It's really very trivial, and everything can be derived from first principles without much effort. If you actually work your way back, look at what I've written on the slides. Questions? Anything on? Yeah, So I either put everybody to sleep or everybody got it, or nobody wants to ask questions. Yes. So, and I can work my way backwards. So, I have the whole thing in painful detail on the slides. But then if you actually look at the backward error propagation rule, if I write it as pseudocode, it's absolutely trivial. I'm going to recurse my way back through the layers. At each layer, I just observe that I'm computing all I'm doing is multiplying the current derivative with the Jacobian and subsequently multiplying that derivative by the weight matrix. I'm just keep going backwards. Now the cool thing over here is that I'm not distinguishing between scalar activations and vector activations. The Jacobian matrix figures it all out. Right? So I can work, and in the process, I can also compute my derivatives with respect to each of my parameters, which I'm going to aggregate for my vector. Question on your face? Oh. Again, observe the analogy to the forward pass. So besides the funky notation of the inverted triangles and the J's, what is happening is pretty much exactly what happens in the forward pass. You have multiplication by a weight matrix, and then you have a processing by a derivative of the activation functions, which is again what happens in the forward pass. You compute an affine combination and process it through the activation function. So in both cases, regardless of whether you write it as vectors or scalars, the forward pseudocode looks a whole lot like the backward pseudocode, except in the backward pseudocode you have this little offshoot which computes derivatives with this. So that's the whole. Okay, so if I were to send myself to for any specific training task, what would I actually be doing? I'm going to be defining my inputs and outputs. Exactly this simple problem, recognizing two or not two. I'd start off with a sigmoid activation. The output is going to be 0 or 1 and something in between. I can use I have to define my divergence, call back lambda divergence for classing. And then I use backpropagation to learn the network parameters. So to learn the derivatives, which I would insert into the gradient descent rule to learn my network parameters. If I were to do something like, and if I were trying to, so if I were trying to do multi-class classification, my output layer is going to be a softmax layer, which is a vector activation, but the rest of the stuff remains exactly the same, right? So at this point, we've sort of gone through this business of how do you actually train a network to learn a function. You define the architecture of the network, you set it up, you have a bunch of training instances, you define your divergence function, define all your activations. And now once you do all of this, we know exactly how to compute derivatives with respect to every parameter. We can accumulate these derivatives and compute the average over the entire training set. And that gradient, that's going to give you the derivative, basically the gradient of the error with respect to all the parameters in my network. I stick it into a gradient descent algorithm, and I learn all of the parameters of my network. Beautiful. Will this always work? So, question so far. I'm going to assume that this is given. I'm never going to refer back to this again. As far as I'm concerned, you know all about training, right? The gradient descent and what it means. We will talk about the implications of this and how you can speed these up in the next, the next 3 or 4 minutes and in the next class. But if I just assume that you got all of this, am I making a mistake? Certainly I am, but which of you will confess to it? Nobody confesses. So let me move on to something more interesting, which is does backprop always work? Will the gradient descent rule always give you the correct answer? So what we're going to look through in the next couple of lectures and the trailing 10 minutes is A. Is this guaranteed to give you a reasonable solution, right? Is it guaranteed to find the solution that you want in the first place? And then issues about how fast will this converge, how can we make this thing converge faster, and what other things might we want to stick into the network to make this entire learning process more efficient. So, but let's begin with the very first issue. Will the backpropagation algorithm always give you the correct answer? Is it always right? So, assuming assuming you find some minimum in the error that you define, right? Will this always give you the answer that you want? So to do this, remember, first, in classification problems, classification error is not a differentiable function. You keep changing your parameters, the error doesn't change. And then you change it a little bit, and one of the instances gets correctly classified. Your classification error jumps instantaneously to some value. And then it stays the same for a while, and so on. So it's not a differentiable function, not a properly differentiable function. Most cases the derivative is 0, and then at some locations the derivative is undefined. So, yeah.
Classification error we define as softmax, right?
No, that's the divergence, which is different from classification error. Classification error is you're counting how many errors you made, right? That we actually came up with a proxy, which was our divergence.
So we're not using the classification error anywhere in our method.
No, we are not. That's the whole point, right? Because if you used it, it's not differentiable and you cannot optimize it. You're just using a proxy to it. And the reason you use the proxy is that you want the proxy to tell you whether your solution is improving or getting worse. Okay? And this is exactly getting to your point, minimizing the divergence, you don't actually minimize classification error. So, why is that? Let me give you a very simple example. A simple perceptron, right? I have a simple perceptron, and it's given these 3 clumps of data. So I have 2 red clumps and 1 blue clump. The red clumps are 1, the blue clumps are -1. I must learn a classifier to separate these 2. Would a perceptron do this? Just using the perceptron rule. If I use the perceptron rule, would I learn to separate these guys? They're very nicely separable, right? I can also prove to you that if I replace this with, say, an L2 divergence, and then using the L2 divergence, these things would be separate. And I can minimize the L2 divergence instead using a softmax for my output. The perceptron that I would learn is going to give me exactly the same solution, or something very similar. It's going to give me a correct solution. But now I do this. I add one little extra training point where I have it on the slide. As far as the perceptron learning rule is concerned, the 2 classes are still linearly separable. It's going to learn to separate them, right? In a finite number of steps. This is what we showed. What about gradient descent? So if I have 1 million of those other guys, how much is this one extra term going to affect the overall loss? Not very much, right? So there's an extra constraint I want to put in here. I'm going to say, as we will see later, I'm going to say that the length of my weight vector is bounded. That doesn't affect my perceptron, right? The perceptron rule is going to find the correct direction, and you don't really care, right? But then, if I'm using the gradient descent rule, this one extra dot, the divergence doesn't affect my overall loss function very much. And so, I get maybe a solution like this. Right? It's not going to change a whole lot. So look at the situation over here. A solution exists, but gradient descent didn't actually find it. The perceptron rule there. Right? And this is part of this is a consequence of something I guess kind of casually stated, that I'm putting a limit on how long the weight vector might be. I don't want infinitely long weight vectors because they don't make sense to me, right? For very many reasons. But anyway, we won't get into that here. But this makes sense. What would happen if I added a training point over there? The perceptron rule would still find correct classifier. Gradient descent is going to wiggle a little bit, right? I put something here. The perceptron rule is going to find a classifier. Gradient descent is going to wiggle a little bit over there. every single case, what would happen is if I have a sufficient number of all of these, sufficiently large number of these other dots, the gradient descent rule is going to wiggle its solution a little bit, but it's not going to go chasing that one dot all over the place. Whereas if you use something more, something explicitly optimized classification error like the perceptron rule, it's going to find the correct solution. Now, is this a bug or a feature? Why?
Yeah, why your data minimizing? No, is the aim of minimizing is
Andrew?
Yeah, I would just say that data point is it's outside the limit of cluster. It's probably noise. It's not actually what you're seeing.
Yeah. So the perceptron, there's a way of stating it. You heard of bias and variance, right? In machine learning, the perceptron rule is unbiased. It will always find the correct solution, but a single point can change blow the solution in different ways, right? The perceptron classifier rule for linearly separable classes has zero bias. But the variance is enormous. Every time you change one training point, it's going to swing all over the place. Whereas backprop is not really going to be affected that much, meaning it has a bias. Anytime you put some constraints on what you learn, it has a bias. It's sometimes even guaranteed to not find the solution, right? On the other hand, it's not going to swing about widely in response to small changes of the input. And I would claim this is a feature, not a bug, right? This is sometimes something that we often want in our learning. But here is a key piece. We just sort of happily use this divergence as a proxy for classification error, and have pretended that it's going to just work. In reality, it's not a perfect proxy. It doesn't, even if you optimize it, the solution that you get is not guaranteed to be the solution that is actually present and that you could find in principle, right? If you used a different optimization algorithm. And how would that be? So why would that be the case? Look at what happens here. So when I use a sigmoid, how far away I am from the training points matters, correct? And if I used this guy, although I'm finding a perfect boundary, the boundary ends up being very close to all of these guys, and I'm going to get penalized for it. Whereas if I'm out here, the boundary ends up being very far away from all of the points except one. I'm going to be penalized by one fellow instead of a whole bunch of guys. And that trade-off is what makes things from swinging around wildly, right? And it makes a difference. So again, this means that if you go off and train your network and you don't find it, if it doesn't find the solution that you expect it to find, because the solution is obvious to you, that may not be because things are going wrong. It may just be a feature of whatever model that you are currently training. Right? And this is for just a single perceptron, but this generalizes to more complex data as well. So let's say I have something that requires a curved decision boundary of this kind, then a single perceptron won't do it. You're going to need a network. But in this case, the network will find a nice little curve, but then I go ahead and add this one little spoiler out here. It's not going to go off and swing around and just change everything. It's going to change it. It's going to just change a little bit from wherever you are and not follow the input. So again, this can be a bug or a feature depending on how you look at it. So backpropagation will often not find a separating solution, even though the solution is within the class of functions learnable by the network, right? And this is because separating solution is not a feasible optimum for the loss function. One resulting benefit is that the backprop trained network has a lower variance than optimal classifier for the training data. I'll stop right here. We're going to give me a couple of minutes because we can pick up a useful in the next class. So in the example, we sort of assume that this objective function that we were trying to minimize had a nice global loss. And even the statement about weighting assumes that some kind of global optimum. But what you often going to find is that hideous functions of this kind. So there's been a lot of discussion of what is the shape of that loss function that we actually get when we are trying to optimize a training for a neural network. And does it have local optima? Does it have only global optima? What about saddle points? So it turns out there's lots and lots of discussion and many hypotheses. The most popular hypothesis currently is that in large networks you have many more saddle points than local minima. Saddle points is things where the error is a minimum in one direction, but not a minimum in other directions. Even if you have local minima, the hypothesis that the local minima are all kind of equivalent. The error at these local minima, the loss at these local minima will be more or less the same. However, for small networks, this is not true. And gradient descent algorithms have this nasty tendency to get stuck both in saddle points, because at the saddle, the divergence is going to be 0, and in local minima. And so, if you actually go through this literature on error surfaces, it turns out to be quite controversial. There are various papers on the topic. Baldwin and Harnick in 1989 say that an NLP with a single hidden layer has only saddle points and no local minima. Profile et al. Say that there are an exponential number of saddle points in large networks. Schaber and Stein et al. Say that for large networks, most local minima lie in a band in fact equivalent. And these guys say in networks of finite size, data finite data can have horrible. I'm not really sure what the final conclusion is. It's all over the place. I think our bottom line is that your training will often not work. Right? Something that you can see. Next class we'll talk about convergence issues, but here's what it covers.